Hello, my name is Tim Pearce. I'm a PhD at the University of Cambridge, and I'm going to be walking you through our AISTATS paper, looking at a new way to get uncertainty estimates out of neural networks. Specifically, what we're going to be doing is taking the ensembling framework and showing how we can make it a little bit more Bayesian. This is joint work with Felix from Prowler and my supervisors, Alexandra, Mohamed, and Andy. So the idea of ensembling is pretty simple. We're going to start off with a small number, say 5 or 10 neural networks. They start from different initializations, and we're going to train them on the same data. So what you find actually is in regions where you have data points, these neural networks tend to hit similar estimates, whereas where you didn't have data points, they tend to keep a bit of diversity. And while this can be used just to improve the accuracy of the whole ensemble, you can also look at the variance or the diversity to look to sort of turn it into a predictive distribution. So you take the mean of the ensemble, so here with J, we're indexing each ensemble member. You then look at the sort of variance of the ensemble, and then you can say, okay, our uncertainty over our prediction of Y is our ensemble variance. So this is your model or your epistemic uncertainty, and then plus some other fixed noise value. And this then gives you a predictive distribution. And the nice thing about this is we've gone from a set of sort of deterministic neural networks that only give you a point estimate to actually having a distribution in the same way as like a Gaussian process would output a full predictive distribution. And the attraction of this method really is that it's very easy to implement, so you're not really changing too much from what you would do with a single neural network. And it scales in the same way. Yeah, the downside is that you have to train M of these, so typically say 5 or 10, and there's kind of no getting around that. But yeah, so there's kind of one big criticism of these uncertainty estimates, which is, I've motivated these quite heuristically, but the question is like, what is the variance of these ensemble like members here? Like, we guaranteed that that's going to be something useful. And I'll show you now a situation where actually this does kind of fail to do what we might want. So here we've got an ensemble of 10 neural networks trained on like a simple regression task. And so the first loss function you might think of using is just to use like a mean squared error. And actually we find that this sort of overfits the data in this perspective, and particularly on the right here, you get this sort of weird extrapolation distribution, which doesn't seem like what we would want. The way of defending against this with a single neural network is to use regularization. So here we're going to think about using L2 regularization. The problem with doing this with an ensemble is that actually you're sort of encouraging all the neural networks to the same sort of single like map solution by doing this, and you actually kill off any diversity, or at least some of the diversity in the ensemble. And if you can compare these predictive distributions to what you would get with a kind of fully Bayesian neural network, the predictions are quite different, right? And I think this is kind of a big argument in favor of Bayesian neural networks to say, well, we do have some sort of, let's say, guarantee about like the quality of the distribution, which we don't necessarily get with an ensemble. And so what we were doing in this paper really is trying to connect these two paradigms up. And so we tried to take ensembling, which kind of has this scalable, easy to implement properties, and we proposed kind of one modification that actually does result in a predictive distribution that is a bit closer to the Bayesian distribution. And the modification is pretty simple, actually. So all we're doing is changing the loss function. And rather than using this sort of regular L2 regularization, we're going to add some randomization. we're going to introduce like the thing that it's regularizing them around. We're going to call this theta anchor J. So each ensemble member is going to have a different draw of this theta anchor J. And it turns out that actually, just by drawing this from the prior, you can end up with pretty reasonable results. And the regularization coefficient is just determined as a function of your sort of data noise that you're assuming in your prior variance. You don't have to take my word for this. So we've put a demonstration online where you can actually choose between the different loss functions and kind of try for yourself. So at the moment we've got the unconstrained loss function, and you sort of find that you get this overfitting behavior. If you switch to a regularized neural network, you sort of lose or kill off all the diversity in the ensemble. Or if you choose the Bayesian estimate, it's sort of, you still have the effect of the prior, but you also kind of keep some of the variance outside of the data. And one of the experiments we did was basically looking at these properties in much more complex environments. So here we trained on certain classes of CFAR10. And then we asked neural networks to kind of predict on out of distribution examples that were kind of progressively further away from the training distribution. And in the extreme case, this was just kind of random noise. And so we looked at like, okay, if we use the anchored loss function that we're proposing versus the like L2 regularization versus like the unconstrained ensemble, how do things happen? And also, so these used 5 neural networks in the ensemble compared to like a single regularized neural network. And what you find is actually, so even when you're showing this completely random noise, like a single regularized neural network, 95% of the time will assign this with high probability to like one of the CFAR classes of like car or frog or whatever. And this reduces down to about 12% if you use the anchored loss function. And so this was done using a VGG, I think it was VGG 13 CNN. Actually, the numbers are even more impressive if you use like a fully connected network. So this was trained on fashion MNIST and tested on similar weird inputs. And in this situation, you actually decrease the these sort of overconfident predictions down to less than 1% on the noise. And I'll explain a bit later on why I think it works so well in this situation. Okay, so we're going to turn our attention to a bit more of the detail now. So far, everything I've talked about has been, I hope, quite intuitive. And we're going to get into a bit of the mathematics for why this loss function might work. And so in this paper, we've actually made a connection with a pretty non-mainstream Bayesian inference technique that we've called randomized map sampling. So this has been explored by a couple of other people, but yeah, certainly not too common. But it sort of takes this idea, so it says, okay, maybe we're in a situation where we can relatively easily get a map estimate of the posterior. So the map estimate is just going to be like a point estimate of your posterior. And the key idea really is to say, well, what if we then add some noise to these map estimates in some way that we can actually create a distribution of these sort of map estimates. And maybe we can think of these this distribution as then like an approximation of our posterior. So that's really the key idea behind what we're going to do. And so if we think about what the maths might look like behind this, so we're saying, okay, we want the map solution is just going to be the argmax of your likelihood times your prior. And if we replace if we say the prior is going to be a normal distribution and we take the log of this, then you end up with, okay, you want to maximize your log likelihood subject to like this L2. This is where the L2 regularization comes from. But here we've left in a sort of non-zero mean. And so the key idea with what we call RMS, randomized map sampling, is to say, well, let's add some noise to this. And what we do is we propose using actually the mean of the prior as the source, as the only source of noise injection. So some other works have looked at adding noise to either the likelihood, maybe in combination with this sort of regularizer. But we say actually we think it's going to be enough just to look at randomizing the mean of the prior. And so this guy that now becomes a function that takes in some random variable. And the key challenge now is to say, well, what distribution do we need to use for these anchoring points in order that the distribution of our function sort of approximates our true posterior? And I don't have time to go through the kind of derivation in full detail, but what we do in the paper is we sort of look at the slightly simplified setting of saying, okay, well, as well as the prior being normally distributed, let's assume that the likelihood is normally distributed in parameter space. And we sort of visualize the algorithm in the paper. But the key result really is that in this situation, your anchoring distribution is also normally distributed, where the mean is just going to be set equal to your prior mean, and your covariance is something slightly more complicated. And there's kind of one more twist in the tail here, in that it turns out that to set your anchoring distribution properly, you need to know the likelihood covariance. And this is a problem because at the point in the process that we're setting the anchoring distribution, we're unlikely to have access to the likelihood distribution. So what we were thinking about in the paper was to say, well, instead of using this kind of full term for the covariance, what if actually we just use this kind of practical workaround where we say, okay, the anchoring distribution is just going to equal the prior distribution. And in this situation, you're no longer kind of going to return the true posterior, even in this normally distributed case. And a lot of what the paper was asking was like, in what way is our posterior now biased, and when is it not? And again, unfortunately, I don't have time to kind of go through the full details, but I think this figure kind of demonstrates the key conclusions that we found. So the first column here is sort of showing a Gaussian prior with the Gaussian likelihood. The second column is saying, like, what does the true posterior look like in this case? Third column is saying, what is the posterior that we recover using this kind of practical approximation with our anchored ensembling approach. And then the fourth column is saying, well, what does mean field variation inference with kind of a diagonal Gaussian return? And so in the first row, we're saying, okay, for the general case, so we have some arbitrary likelihood, which leads to some arbitrary posterior. In this situation, the posterior that we're going to return will have underestimated marginal variance, and the correlation will be overestimated. And I think in this situation, actually, mean field variation inference kind of looks quite favorable because it kind of keeps that marginal variance a little bit better. But we also look at these two special conditions, and in particular this condition one, where we say, actually, if you have perfect correlations within your model, your likelihood is going to be this kind of very long and skinny. And this is going to lead to a very sort of skinny posterior. And in this situation, actually, RMS gives you a very good recovery of your true posterior. And particularly when you compare it to like what mean field variational inference does, where you're just kind of taking this, kind of just becomes like a point estimate almost of your posterior. And then alternatively, you could think about extrapolation parameters where these maybe have a very wide likelihood variance. And in this situation, all the methods are able to recover the true posterior. And I think the thing we spend a bit of time in the paper talking about is arguing that actually, particularly in wide, fully connected networks, you have a lot of of B and C parameters. And I think that is then why, if we look at the predictive distributions produced by different methods, so the left two here are kind of exact Bayesian inference methods that don't scale so well. These mean field and MC dropout are sort of more scalable approaches, but they start to lose the interpolation uncertainty. So they do okay with the extrapolation, but they start to lose the fidelity in this sort of interpolation regions. And actually our method tends to at least qualitatively recover the sort of true, they seem to be closer to the kind of true Bayesian predictive distributions. And we have plenty more experiments that investigate this in a bit more detail in the paper. So thank you very much for listening. Feel free to get in touch if you have any questions about this.